So, in our last meeting, we found the 15 microstates for the P2 configuration, such as would be found in atomic carbon. We found the 15 microstates. We learned how to do an M sub L, M sub S diagram. And we extracted several terms, and we learned that the 15 microstates are broken up into 3 terms, and we rank those terms in order by Hund's rules at the very end of the hour. And so what I want to do is kind of carry on from this point to the next point, and you kind of need what we're going to do next to interpret the sodium spectrum that you recorded in the laboratory. Let's start by just enumerating the rules. The highest value of the S value means you have the lowest energy. So that's why the triplet P is lowest. And if S values are the same, highest L is lowest energy. So where we were left with last time, the triplet P is lowest because the spin is 1. Remember, this term is 2s plus 1, the so-called spin multiplicity. Now, for these, S equals 0 for both of them, so the spin rule doesn't help us. But for a triplet D, L equals 2, and for a triplet S, L equals 1. So this, I'm using the second rule to get these two in order. So let's stop for a minute and see if you can explain this to me. So we'll start with you, Ed. Why is the triplet P the low? So we have an energy scale going up like this. So why is the triplet P term the lowest in energy?
I don't know, because the energy gaps are smaller between one another.
Okay, then we have 2 rules that guide the ordering. Here they are. The term with the highest capital S spin quantum number is the lowest energy one.
Okay.
And remember, these terms are in the form 2s plus 1 raised to the L power, and L is enumerated by letters S, P, D, F, G, and so forth. L equals 0, 1, 2, 3, 4, and so forth. So this is a triplet because S equals 1 and 2s plus 1 equals 3.
Okay.
So this one's lowest because of the first rule. It has the highest value of the spin. These are the 3 terms we got from our work yesterday.
Yeah.
Or on Tuesday. Now, what's that? Explain why I put the singlet D below the singlet S.
So that's the second rule, because the singlet D has a higher L, so lower energy.
Right. So now we have our 15 terms are grouped into 3 our 15 states that we had, all the Pauli allowed states are grouped into 3 terms that are in this order of energy.
So what's that telling us for carbon then? Because this is for carbon, right?
Right, so this is for so for an atom, an isolated atom of carbon, in a P2, both electrons in the p orbitals will have these 3 states.
Okay, so electrons in the p orbitals can have like a single.
They could be triplet P's, they could be singlet D's, or singlet S's.
Okay, that's why I was getting confused because it's like p electrons, but they can have a s or a d.
Right, and the lowest energy is triplet P, so if we
Yeah.
just could make atomic carbon, and there are ways to make it, isolate, it would be paramagnetic, it'd be a triplet P. So, let's look at our terms. Once again, I'm going to do some other stuff. Terms are triplet P, singlet D, and singlet S in that order of energy. Now, number of states in a term equals 2s plus 1 times 2l plus 1. This is called, so we figured that out last time by, we have 15 total, but for a singlet S, 2s plus 1 is 1, and 2l plus 1 is 1, so there's only one state for singlet S. Now, what about for singlet D? Let's go to Ed and see if he can do singlet D.
So S.
So for a singlet, S equals 0.
Yep.
So what's 2 times 0 plus 1?
1.
1. And for D, what do we
4
have?
plus 1.
Okay, for a D orbital, or a D state, L equals
2.
2. So what's 2 times 2 plus 1?
5.
5. And now we'll go over to you, psi. So here S equals 0, S equals 0, L equals 0, L equals 2.
For singlet S, doesn't L equal 1?
Yeah.
So what did it be? 2?
Okay, so
3.
what's 2 times 1 plus 1?
Hold on. Okay, 2 times. Okay.
Because S equals 1 for this one.
So, yeah, so it's going to be 3.
So this would be 3. What about for L?
Well, L is 1, so that turns out to be 3 times 3.
Now, if you add those up, how many do you get?
9. Oh, 15.
15. So the 15 microstates break up into 3 terms.
Would it? S1. Doesn't L equal 1? So 2 times 1.
Oh, for an S-type angular momentum, L equals 0.
Okay.
So it's wrong up there at the top then where it says L equals 1.
Oh, yeah, L equals 0. Absolutely. Okay. I'm gonna write some stuff, then we'll do it. Okay, the first one we're going to do is we're going to assume that the spin and the orbital angular momenta do not couple. What that means is if you go on the teacups at Disneyland, the angular momentum of the individual teacup versus the platter, they're not going to interact with one another. Now, in reality, they will, and that's why we get the sodium doublet. But we're going to write all the microstates of these terms without spin orbit coupling. This is the so-called uncoupled representation. And we'll do the Dirac notation. By the way, here we're going considerably beyond what's in our textbook. So you're getting more for your money here. Okay, shall we start with the singlet S?
Sure.
Okay, so the states will be characterized by 4 quantum numbers: capital L, capital S, M sub L, and M sub S. So for the singlet S term, there's just one state. There it is. And for that singlet S, what does L have to be?
0.
0. What is S?
Oh, that's going to be 0.
What is M sub L then?
0.
What's M sub S?
0.
So there's the state that there's just one wave function that does it, and all the L, S, M sub L, and M sub S are all zeros. And notice you only get one. And we've written down in the Dirac notation what that is. Now, with singlet D, it's a little bit trickier. And I have this pattern here. So what do I do for singlet D? What's L for these D terms?
2.
2. What's S?
0.
What's M sub S?
0.
0. Now, what values of M sub L are possible? If L equals 2, how many values of M sub L do we get?
5.
Well, isn't that interesting? So this is 2, 0, 2, 0, 2, 0, 1, 0, and now give me the other 3.
So you got 2.
I'll give you 2 and 0.
0, 0.
0, 0. Keep on going. 2, 0,
Negative 1, 0.
negative 1, 0, right? And what's our last one?
2, 0, negative 2, 0.
Negative 2, 0. So these are the 5 individual quantum states that go with a singlet D. And the 1 quantum state that goes with a singlet S. So these 5 quantum states have the same energy. So have same energy. In other words, they're degenerate. And so the singlet D term is composed of 5 quantum states. And they have the same energy, therefore they're degenerate. This one is just one quantum state. And it has a higher energy than the singlet Ds. Now, what's the last one? Okay, so triplet P. So L is 1, S is 1. Now, I recommend that you be systematic about this. M sub L can go between +1 and -1 in unit increments, and so can M sub S. So why don't we leave M sub L equal 1, and M sub S can go 1, 0, -1. Then we'll do 3 more. 1, 1. And then I'm going to go to 0. 1, 1, 0, 1. 1, 1. 0, 0. And 1, 1, 0, -1. So I'm choosing a given M sub L, and I'm systematically varying the M sub S. And there are other ways to do it symmetrically. And let's see if you could do the last one. It's 1, 1, -1, and now what do I do?
+1.
Yeah?
1, 1, -1, 0. And 1, 1, -1, -1.
There are the 9. So here are 9 quantum states. Same energy. None of this has spin orbit coupling. We're treating the orbital and the spin angular momentum as completely independent. They don't interact one with another. And we were able to write all the quantum states associated with each of these terms. Okay? So this quantum state will have an energy that depends on L being equal to 0 and S being equal to 0. This one will have one L equals 2, S equals 0. There'll be 5 of these with these energy. And this is L equals 1, S equals 1. So degenerate means more than one quantum state for a given energy. Now, stop right here, ask me questions. Is this making any sense at all? So we're building again on what we did in the last lecture.
Makes more sense than a lot of other things.
In this course, probably.
Yeah.
Okay. Now, are you ready to have spin orbit coupling? Well, I don't care whether you're ready or not, you're going to get it. And by the way, we're going to have a short lecture today because I have an engineering meeting that I have to go to at 3 o'clock. So, but we're actually making excellent progress in what we needed to cover today. Okay, so this is without spin orbit coupling. But now I'm going to show you spin orbit coupling, and that's
write them all out?
What?
You gonna write them all out like this?
There'll be 15 of them again,
Yeah.
but they'll be in a totally different way. So this is the uncoupled representation. But it turns out the spin.
You usually don't see the uncoupled
So,
variety.
yeah, I mean, it's close. At the top of the periodic table, the spin orbit coupling is a lot less than as you go down the periodic table. But there's enough coupling so you can see it in sodium, if you look. Okay. Atomic terms with spin orbit coupling. Now it makes sense that if you're riding the teacups at Disneyland and the platter's moving and there's one platter inside another platter, there's 3 angular momenta actually. We know it couples. If you don't believe me, look at all the barf that they have to blow out of there every day. Okay. So, coupling. Okay. So, define a coupled quantum number J, which could take on the values of L plus S minus 1, all the way down to the absolute value of L minus S. So this is the new quantum number that we're going to deal with. And now our quantum states. Now, we may not want to deal with a coupled representation, but if the atoms are coupling their angular momenta, we have to. In other words, this isn't a preference, this is a necessity. Quantum states with SO, spin orbit coupling. Okay, they're going to be in the form LSJ M sub J. And J will always go between M sub J, will always go between plus J and minus J. So we have a different set of quantum numbers, as you can see here. So let's start with the singlet S, where L equals 0 and S equals 0. Well, if L equals 0 and S equals 0, convince yourself that the only possible value of J is 0, and the only possible value of M sub J is also 0. So this quantum state looks like, for singlet S, 0, 0, 0, 0. Now, we have a different set of quantum numbers, but they're all zeros again. Now, let's go to the singlet D. Well, for singlet D, L equals 2, S equals 0. The only possible value of J is 2, and M sub J can take on the values minus 2, minus 1, 0, 1, 2. Because L minus S and L plus S have to be the same value. If L equals 2 and S equals 0. And so we're going to have 5 states. L equals 2, S equals 0, and now J can equal 2. And M sub J can take other values 2, 2, 0, 2, 1, 2, 0, 2, 0, 2, 0, 2, minus 1, and 2, 0, 2, minus 2. How many quantum states are there? 5. Interesting. So 1 quantum state for the singlet S, and there are 5 quantum states for the singlet D, all the same energy. Now, how many quantum states do you think we're going to find in the coupled representation for,
9.
yeah, we're going to find 9. But there's going to be an interesting additional splitting. And this additional splitting is what we're observing when we observe the sodium doublet. Okay, so we're working this all around. We're kind of giving you the theoretical background so you can understand the sodium doublet spectrum. Okay, so we've done singlet D. Now let's do the singlet P. And the singlet P has L equals 1 and S equals 1. So what are the possible values of J if L and S both equal 1?
2, -1, and 0.
2, 1, and 0. Because,
Oh, it can't be negative.
yeah, it can't be negative. J can take on 3 values, 2, 1, and 0.
Okay.
Okay? So here, let's do singlet P 2. It'll be of the form L, S, J, M sub J. So L equals 1, S equals 1, J equals, so I'm going to choose the 2 first. J equals 2, and M sub J can take on the values 2, 1, 1, 2, 1, 1, 1, 2, 0, 1, 1, 2, minus 1, and 1, 1, 2, minus 2.
Shouldn't that be triplet P? It's a singlet P up there.
Oh, it should be a triplet P. Exactly right. Okay. This subscript, this is the J value. So for this particular value of J, how many microstates did we get?
6. Or 5, sorry.
We got 6, right? Or is it 5? No, we got 5, right? So we have 5 microstates. Okay, now we have the 1 quantum number for J. So this is a triplet P1 with J equals 1, L, S, J, M sub J, 1, 1, 1, and now M sub J can take on the value 1, 0, 1, 1, 1, minus 1. So there are 3 microstates here. And then we have one more, triplet P1, or triplet P0, J equals 0. And this is 1, 1, 0, 0. This is 1 microstate. And when we do the spectroscopy, we see evidence, in other words, the coupled representation is what we see. not the uncoupled one. So we have some different energies in here. Now, we've come to a very nice stopping place, and this is good because I'm going to stop just a little bit early because I have to get ready for this engineering meeting. But at this point, we have derived for carbon the complete spin orbit picture for a 2p2 electron configuration, both without and with spin orbit coupling. And this places us in our very next meeting to talk about the interactions of spin orbit coupling and where that sodium doublet comes from and everything. You're going to be getting some handouts in the immediate near future.